measured that are unbiased. So, after having discussed sample proportions, proportions summarize categorical variables, means summarize quantitative variables. So as we get into some of the processes here, they're going to start mixing and matching the different types of problems. You need to be able to verify what type of sampling distribution you're working with, whether it has to do with proportions or means. And so one of the ways to distinguish there is to determine what type of variable you happen to be working with, whether it's categorical or quantitative. Now with means, not only can we use essentially the exact same concepts as we use with proportions, but we can use almost the exact same model. So yesterday when we talked about proportions, knowing the population proportion allowed us to calculate the standard deviation for the sampling distribution. Knowing P allowed us to find the standard deviation for our distribution. Means don't work the same way. Now, one of the things to note here, the mean of our sampling distribution, which is going to be denoted mu sub x bar. So just like we had mu with the subscript p hat for sample proportions, now we're talking about sample means, so mu of x bar will be equal to the population mean. So within the problem, they're going to tell you what the population mean should be. Now, the standard deviation of our sampling distribution, which is going to be denoted with the lowercase sigma subscript x bar, again because we're talking sample means. That is going to be calculated by taking the population mean. So, within the problem, two of the things they're going to have to give you, what's the population mean and what's the population standard deviation. But you're going to take that population standard deviation and divide by the square root of your sample size. So if you were given a situation where you had a distribution that has a mean of 50 and a standard deviation of 10, and they say you're going to start taking a sample of size 12. So if you had a sample of size 12, to find your standard deviation for your sampling distribution, you would take the population standard deviation 10 divided by the square root of the sample size 12. So one of the things that you have to be careful with, and this is where most people make their biggest mistake, when they get a mean and standard deviation in the problem, they just use that mean and standard deviation for their calculations. That only works if we're talking about the population in general. But if we are talking about a sampling distribution based on a certain sample size, that standard deviation needs to be recalculated before we can use it. So take the standard deviation they give you, divide by the square root of the sample size. That's the standard deviation you're going to use for your particular problem. Okay. Notice also what type of distribution are we mostly going to be working with. Normal. Those are the ones we're looking for. Okay. So, the fundamental theorem of statistics. The sampling distribution of any mean becomes more nearly normal as the sample size grows. Now, there's lots of situations that can arise from these sampling distributions. So, for instance, our population distribution can be any shape. It can be skewed right, skewed left. It could already be normally distributed, so it could be symmetric. But if we take a sampling distribution, so if we start taking samples over and over from our population, as the size of our samples increase, the more normal our sampling distribution will become. Now, this is true as long as observations are independent and we collect them using randomization. And again, that independence portion is sometimes a little difficult to come by definitively within a given scenario, so we're going to have conditions here in a second that allow us to kind of account for that part of our assumption. Now, the other kind of neat thing about this fundamental theorem of statistics is it doesn't matter what our initial population distribution looks like. Whether it's skewed, slightly skewed, symmetric, whether it's uniform, it does not matter what the original distribution looks like. As we continue to take larger and larger samples for our sampling distribution, we are going to be creating more and more normal distributions. So one of the things you'll see here, this fundamental theorem, is sometimes called the central limit theorem, or CLT, as you'll see in the abbreviations. So you might run into questions that ask you something about what's the idea behind the central limit theorem of statistics, or the CLT. Well, the main idea is if you take larger samples from a population, the sampling distribution created becomes more nearly normal. Now, assumptions and conditions for sampling distributions involving means. So our CLT requires almost the exact same assumptions and conditions as we saw for proportions. So these are ones we saw yesterday. The independence assumption was that the sample values must be independent of each other. The sample size assumption, the sample must be large enough. So these are not new. Okay? Again, the assumptions themselves can be sometimes tricky just to attack as they are, which means we're going to talk specifically about the conditions needed. So this is the part that you definitely need. In order to work with a normal distribution involving a sampling distribution for the means, we need to make sure that our randomization condition is met. So our sample should be a simple random sample from the population. Again, that should be specified somewhere within the question. If it's not, then you have to kind of examine for yourself, do you feel the sample would still be representative or not? If it doesn't specifically say also, you can go ahead and say we're going to assume they took a random sample and then make that a big note so that the people reading your results know that this may not be from a random sample, which means these may not be the most accurate results. The 10% condition is exactly the same. The sample size cannot be larger than 10% of the population. Now, the large enough condition is where we talk about the shape of our sampling distribution. So just like yesterday with the success fail or normal or large counts condition, that determined the shape. So random and 10% kind of accounts for our independence. The large enough sample condition accounts for the shape, the normality that we're looking for. So there's kind of two things to consider here. If our population distribution is normal. So if they start off the problem saying the distribution of these values is normal with this mean and this standard deviation, then regardless of how big your sample is, your sampling distribution will be normal. So if you're sampling from an already normal distribution, you're going to continue to create a normal distribution. If the distribution is not normal to begin with, so if they tell you something to the effect that the distribution is skewed or something of that nature, now we need to think about what our sample size looks like. So if it's not normal to begin with, in order for us to assume normality, we need to have a sample size of at least 30. So as far as conditions go, these are pretty simple to check. The random, they pretty much tell you in the problem. The 10%, all you got to think about is this sample likely less than 10% of the total population? And then for the large enough sample, is my sample at least 30? If that's the case, I'm good to go. If my sample is not 30 or more, then I have to think about what the original distribution looks like. So that's the only thing that can be a little bit tricky, is when you have samples that are less than 30 for these sample means. Okay. So let's go through an example. Suppose that the number of texts sent during a typical day by students at a large high school follows a right-skewed distribution with a mean of 45 and a standard deviation of 35. How likely is it that a random sample of 50 students will have sent more than a total of 2,500 texts in the last day? So, if we're taking a look at this problem here, a couple of things that we want to start looking through or sifting out is some of the important information. So it says the distribution is a right-skewed distribution. So our population distribution is not normal. Okay, so that's something to keep in mind. It has a mean of 45, so what is that actually telling us? What mean is that referring to?
Population.
The population. Okay, that's the population mean. Mu is 45 texts per day. Then it says the standard deviation is 35. Well, this 35 refers to which standard deviation?
Population.
The population again. So they have told us both the mean and the standard deviation for the population. Okay. Now, if we know what the mean for our population is, what is the mean of my sampling distribution? So what would mu sub x bar be? So if I take my sample, because now we're looking at a sample of 50 students, right? So if we take a sample of 50 students, now we're basing everything on a sampling distribution where samples of size 50 were taken over and over and over again. It should be exactly 45. Okay, so knowing the population mean automatically gives us the mean of our sampling distribution. What would the standard deviation of our sampling distribution look like?
35.
And what is n?
N is 50.
Okay, so since we're taking samples of size 50, our standard deviation for our sampling distribution becomes the population standard deviation 35 divided by the square root of our sample size, 50. So in your calculator, someone work that out real quick. What's the decimal? Give me like
4.949.
Okay? So we get a standard deviation of about 4.949. Now, before we go any further, so we know what the mean and the standard deviation of our distribution should look like, or should be, but before we go any further, what should we check? Our conditions. Make sure we know kind of what we're dealing with here. So, if I check my conditions, remember you can just kind of list them out and make comments on each. So, do we have randomization employed? Yes, and what tells us that?
Random sample.
That's random sample of 50 students. Okay. The next one was our 10% condition. So our sample size is 50. Is it safe to assume that 50 students is less than 10% of all students at a large high school?
Yes.
Yes. So that's the key here, is that it's a large high school. So 50 should be less than 10% of all students at a large high school. Okay? And the way to kind of think about that is 50 is 10% of 500. Is it likely that there's more than 500 students in a large high school? Yes. Okay? The last one is the large sample condition. Now here we do have to be careful because they told us specifically that our population distribution is not normal. So if that's the case, what was our cutoff for an acceptable sample size? 30. So 50 is greater than or equal to 30, which means we do have a normal distribution. Or, I shouldn't say normal, it's just an approximately normal distribution. Okay? So, we've checked our conditions. We have kind of the main things that we need here. We have the mean of our distribution, we have the standard deviation of our sampling distribution. Now what we're missing is what value we're looking at. So we're saying how likely is it that a random sample of 50 students will have sent more than a total of 2,500 texts in the last day? So what we're missing now is what our sample mean is.
Why do we use success fail condition?
Success fail is for proportions. For the mean, we call it large sample. So what is my X bar, my actual sample mean? Say what? Well, 45 is my population value. That's the center. So think about what these mean, what this mean and standard deviation mean. They're saying that in a group of students, generally, there are 45 texts sent per day per student. Okay, so each student would send about 45 texts per day. Now what we're asking is, how likely is it that in our sample of 50 students, more than a total of 2,500 texts were sent in that day? So it'd be 50. If there's 2,500 texts for the entire group of 50, the average number of texts would be 50 texts per student. Does that make sense? 2,500 divided by 50. Yep. So we're just calculating an average. So it's like we added up all the texts. So there's 2,500 total, divided by the 50 total students. About 50 per student is what we're looking at. Now, here's the thing to think about on this case. The way I'm solving it right now, I kept my mean and standard deviation as 45 and 35. So 45 texts per student with a standard deviation of 35 texts per student. I used the mean then, so since I was looking at a total of 2,500 texts out of 50 students, that meant 50 texts per student. The other thing I could have done with this type of problem is I could have left my sample mean at 2,500. But if that's what I'm going to do, then I have to convert my original population mean and standard deviation to reflect that now we're not doing per student, we're doing totals. So instead of 45 texts, I would take 45 times 50, my sample size, and that would tell me how many total texts per day are sent. I would then take my standard deviation of 35, multiply it by 50, that's my total standard deviation. Do you guys understand that? And on these types of problems, it does not matter which way you go. So whether you do it the way I have it set up here, or whether you convert everything to total number of texts, you're going to get exactly the same numbers regardless. Okay? So that's just something to kind of keep in mind here. So now, if I'm looking here, I'm saying how likely is it that a random sample of 50 students will have sent more than a total of 2,500 texts? So basically we're asking what's the probability that X bar is greater than 2,500. So what's the probability that if we take a sample of 50, we find a group that has more than 2,500 texts sent? Oops, I said 50 and wrote 2,500.
I hate it when that happens.
Okay, so in this instance then, since we know we're dealing with a normal distribution, that means we need to convert to a z-score. So z would have to be greater than, we take the actual sample mean, 50, minus the actual mean for our distribution, 45, and then divide by our standard deviation, which was the 4.949. So, at this point, we're finding our z-score. When we plug in then, so 50 minus 45 divided by 4.949. So you get a z-score of about 1.01. So then at this point, you would either look up 1.01 on your table, or you would plug into your normal CDF function on your calculator, and then find your proportion accordingly. Now, if you were looking up on the table, when you get the proportion from the table, what would you have to remember to do? Subtract from 1. This is a greater than. We have to subtract from 1 from the table. If you plug it in your calculator, you would put 1.01 as your low bound. Your upper bound then would be positive 1 to the 99, and then it's going to calculate the exact value for you. And so when you do this, you get a value of about 0.156 or something around there. Okay? So basically, to answer the question then, there's about a 15.6% chance that a random sample of 50 students will have sent more than 2,500 texts in the last day.
Does this work with weather?
With weather?
Yeah, like could you do the same thing using the nation as population available out of the sample and predict how much white rain or snow you're going to get?
You can. Generally with weather, they base their probability. So when they say like there's a 30% chance of rain, they're not basing it off of like other locations. Results, what they're doing is they're almost like running simulations. Like they input the information like barometric pressure and moisture content and things like that. And they run simulations. and like they do like 50 simulations of what would happen given this particular information. They say in 30% of those 50, it rained or something like that. Or so like when they're making these predictions like tomorrow, having how much snow we have, they put all the information they get in. Based on those simulations, they're saying that there's this % chance that we get this much snow. In some of the simulations, we got this much snow, and so that's kind of what they're reporting there. So it's not quite the same.
But I could do is figure out how much we're gonna get.
You could. All right. So, last couple things here. Just some last minute cautions. So these are things like what can go wrong with things you do with the sampling distributions here. So the first one, don't confuse the sampling distribution with the distribution of the sample. Okay? So let's think about what that means here. Your sampling distribution, or I guess kind of explains right here. When you take a sample, you look at its distribution, usually with like a histogram or a dot plot or something like that. And you may calculate summary statistics. So, in that last example we did, the sample mean was the 50 texts per day per student. Okay? That came from the one single sample of 50 students that we took. That's the distribution of the sample. The sampling distribution is essentially an imaginary collection of values that the statistic might have taken for any other random sample of 50 students. So the distribution of the sample is you've collected a single sample, you have identified its distribution and calculated whatever you need to from that. The sampling distribution is if I continue to sample over and over and over again, what are the summary statistics going to start looking like? Okay, so that's a big difference there between those two, even though they look and sound exactly the same. The next thing, always be aware of observations that are not independent. The CLT, so that's the fundamental theorem of statistics, depends crucially on that assumption of independence. You can't necessarily check it with the data. You have to think about how they're gathered. The biggest thing to counteract or make sure you're not making the mistake is make sure you go through those conditions very carefully. And then make sure small samples can be a problem. Make sure your sample's large enough or you know that the original distribution was normal to begin with. Okay? So here are the problems you need. Now, we went